Let us now look at some examples. Example 1 says a slit of width d is illuminated by a monochromatic light of wavelength 7 nanometer at normal incidence. Calculate the value of d for position of its first minimum at an angle of 30 degrees. Here it is a single slit, so it is based on diffraction, and we know that in case of diffraction the condition is for minimum, the condition is d into sine theta is n into lambda, where n is equal to 1, 2, 3, etc. This is the condition for minimum for diffraction in case of path difference. The question says calculate the value of d for the position of first minimum, which means here n becomes 1. So d into sine theta is equal to lambda, and also here the angle theta is given as 30 degrees. So d into sine 30, which is half, that is equal to lambda, which is 700 into 10 power minus 9, because it is nanometer. We need to find d. So d from here is equal to 2 into 700 into 10 power minus 9. That will be 14 into 10 power minus 7, because we can write this as 10 power 2. So 10 power minus 9 plus 2 will be 10 power minus 7, or we can write this as 1.4 into 10 power minus 6 meter, or d is equal to 1.4 micrometer. We have seen in theory class that the slit width is very small, only then we get a pattern of alternate dark and bright bands, and as seen here it is of the order of micrometers. Example 2 says the diameter of the objective of telescope is 1.5 meter. If the mean wavelength of light used is 6200 angstrom, compute. There are two parts in the question. Part 1 says the smallest angular separation of two stars which can be resolved by it. Second part is the resolving power of the telescope. We learnt in theory class that in case of a telescope, the limit of resolution, which is called as d theta, this limit of resolution is the minimum angular separation that the two objects makes with the eye. For example, if we call this as object A and object B, these objects will make some angle with the eye or the objective lens called as d theta. Now for them to be seen separately or for them to be just resolved, the angle d theta should be equal to 1.22 lambda by 2a. Keep in mind that 2a here is the diameter of the objective. So putting it back, d theta is 1.22 into lambda is given as 6200 angstrom. We can write this as 6.2 into 10 power minus 7 by 2a is 1.5 meter, and if you put it back here, this is equal to, it will be 7.564 by 1.5 into 10 power minus 7, which is equal to 5.04 into 10 power minus 7, and this d theta is measured in terms of radians. This is the first part. Second part says find the resolving power of the telescope. Resolving power, which is called as Rp, is defined as 1 by d theta, and that is equal to 1 by 5.04 into 10 power minus 7, that is equal to, it will be 1.5 0.98 into 10 power 6, because it becomes 0.198 into 10 power 7. If you take out 10 power here, it becomes 1.98 into 10 power 6. It will be per radian. So this is its resolving power. Example 3 says, what is the minimum distance between 2 points that will permit them to be resolved at 2 km using a terrestrial telescope of 6.5 into 10 power minus 2 diameter objective at wavelength of 5500 angstrom. So what is given here is, there are 2 points. The 2 points are very far away, and the distance between the object, it says what is the minimum distance between 2 points that will permit them to be resolved at 2 km, which means the objects are at a distance of 2 km from the objective or the human eye. Suppose somewhere here an objective lens is placed. Let us call the objects as A and then B. The distance between the objects and this point is taken as D. Now somewhere here is the objective. This angle is called as d theta, and we know what is d theta. But here question says, what is the minimum suppression that will permit them to be resolved, which means here we need to find what is the distance between two objects, which we call as x. So we need to find out what this x is in this case. And we know that if you have a telescope or objective here, then the limit of resolution is given as 1.22 lambda by 2 into a. Now here lambda is given as 5500 angstrom, and also the telescope as diameter as given here, it says using a terrestrial telescope of 6.5 into 10 power minus 2 diameter objective. So in this case 2a is given as 6.5 centimeter. That's the meaning of this. Putting it back here, we can say d theta is equal to 1.22. We just rewrite it. 1.22 into lambda here is 5.5 into 10 power minus 7 by 6.5 into 10 power minus 2 meter. Just come back to a minute. And also let us find what is x. Now since it is far away, we can think that this is part of a circle. In that case, you can use the relationship between arc distance, the angle and the radius. So this capital D acts like a radius. So from here x is equal to d theta into d. This would mean that d theta is equal to x by d. So putting it back here, x by d is equal to this formula, that is 1.22 into 5.5 by 6.5 into 10 power minus 5. X is equal to capital D, which is distance between the object and the eye, which is given as 2 km here. So cross multiplying, we get 1.22 into 5.5 by 6.5 into 2 into 10 power 3 into 10 power minus 5. That is equal to, it will be 13.42 into 10 power minus 2 by 6.5, which is approximately equal to 2.065 into 10 power minus 2 meter, or 2.065 centimeter. So this is a required answer. Again, don't copy as given here. Solve on your own from the formula given and verify the answer, because the way of solving would vary. Some students may solve it here only, they may solve directly and just keep a number here. Some would solve here, it depends on student. So in such numericals, there's a need to copy step by step. Look at the formula given here and look at the principle beyond this, and then verify the answer which is given here. If need be, a student can pause the video also before starting numerical. Pause the video, read the question once or twice, solve it, and try to verify the answer given here. If a student doesn't get the solution, then the student can look at how it has been worked out. Example 4 says, light of wavelength 5893 angstrom is used in an experiment with a microscope. If the semi-vertical angle is 50 degrees, calculate the limit of resolution and resolving power of the microscope. Again, this is based on direct formula substitution. The limit of resolution, which is called as d theta or dx in case of a microscope, this dx was given as lambda by 2n into sine beta. This is 1.22 into lambda. It is equal to 1.22 into lambda here is 5.893 into 10 power minus 7 by 2 into, here nothing is given about n, so we can take n to be equal to 1 into sine 50 degrees. 1.22 into 5.893 is equal to 7.189 into 10 power minus 7 by 2 into sine 50 would be, if you use a log table, the answer of sine 50 degrees would be, it is 0.7660, and if you solve it further, 2 into 0.760 will be equal to 1.532. Therefore, dx is equal to 7.189 into 10 power minus 7 by 1.532. That is equal to 4.692 into 10 power minus 7 meter. There is a printing mistake here. Please ignore this. I mean typing mistake here. And the resolving power is the reciprocal of limit of resolution, that is equal to 1 by 4.692 into 10 power minus 7. So it goes on top, it becomes 10 power 7, and 1 by 4.692 is equal to 0.2131. Therefore, resolving power is equal to 2.131 into 10 power plus 6 meters per meter. Example 5 says, limit of resolution of a microscope in air is 2.4 into 10 power minus 7 meter. If the semi-vertical angle is 52 degrees, then calculate the wavelength of light used. Second part says, what will be its resolving power? Here we need to find resolving power. What will be its resolving power if it is immersed in a liquid of refractive index 1.42? So there are two parts here. The first part is to find the wavelength given the limit of resolution. So here we know that the limit of resolution dx is given as 1.22 lambda by 2n into sine beta. In the first case, nothing is being mentioned about the medium, which means we can take n is equal to 1 in the first case, and we need to find the wavelength. Therefore, from here, by cross multiplying, we can say lambda is equal to 2 into sine beta into dx by 1.22, and that is equal to, it is 2 and sine of 52 degrees. So sine, and write it here, sine 52 degrees is equal to, it is 0.7880, so it will be 0.7880 into dx, which is the limit of resolution, which is given as 2.4 into 10 power minus 7, that divided by 1.22, and is equal to, lambda is equal to, so 2 into 2.4 would be 4.8 into 0.700 is equal to 3.7824 into 10 power minus 7 by 1.22, and this is approximately equal to 3100 angstrom. It will be 3.1 into 10 power minus 7 meter, which is 3100 angstrom. Second part says what will be its resolving power. So here we need to find its resolving power if it is immersed in a liquid of refractive index 1.42. So resolving power is given as, it will be 2n into sine beta into 1.22 into lambda. Here the angle remains almost same, and now it is immersed in a liquid of refractive index 1.42. So here what we get is, it is 2 into 1.42 into sine 52 degrees by 1.22 into, we can write this as 3.1 into 10 power minus 7, so that it becomes easy to simplify. The resolving power from here is equal to, so it will be 2 into 1.42 into sine 52, which is 0.7880, that is equal to 2.238. This becomes 10 plus 7 in the numerator by 1.22 into 3.1 is equal to 3.782. Resolving power is equal to 0.592 into 10 power 7 per meter, or we can write this as resolving power is equal to 5.92 into 10 power 6 per meter. So this is the required answer.